Hi, my name's Dr. Adam Booth and welcome to another online edition of Quantum Source. Now, if you're new to Quantum Source, then your first question might be, what is Quantum Source? And that's a very reasonable question. Quantum Source is a brilliant blend of fascinating research facts to nourish your mind and keep you educated and entertained. And we were doing this throughout the lockdown summer. We had a lot of research videos that were released and you can track them all down through our Quantum Source Twitter and Instagram feeds. But for this little series of Quantum Sources, we have teamed up with the University of Leeds' Be Curious project, which means that we get a corner banner as a souvenir. Hey! And what we're talking about today is potential solutions to our continuing problem as a society with the emission of carbon dioxide. Now, although we have a lot of potential renewable solutions to our energy needs, while we're bringing them online, we're still burning fossil fuels and we're still emitting carbon dioxide, and that is contributing to global heating. One potential solution that we have is to take that carbon dioxide and store it underground. And today's speaker, Professor Chris Rayner, is an expert in doing just that. He's a Professor of Organic Chemistry in the University of Leeds' School of Chemistry, and we're going to be giving him a call in just a second. Now, the other thing about Quantum Source was that there's always a recommendation that fascinating facts are best served with something refreshing, and so my own little refreshing source for this talk is a celebration of the fact that we can store carbon dioxide and do something much more useful with it rather than just emit it, and it comes in the form of a Citra beer from our local salt beer factory. So you get yourself something nice and we'll give Chris a call. Cheers. And good afternoon, Chris. Welcome to Quantum Source.
Hi, Adam. Nice to see you.
Absolutely. You too. And how are you doing?
I'm doing really good, thank you. Very good.
Cool. Now then, before we talk too much about chemistry and the science of carbon capture, I've got myself a recommended source here that involves a little bit of carbon dioxide. Can you recommend me a source?
I can recommend you a source, and what I'm going to do is tell you all about it during my talk. So there'll be some information about our secret source, and I'll tell you all about it in the talk.
All right, sounds great. Can't wait. And again, just before we get too far into the science that you're working on at the moment, could you just tell us something about how you got curious in chemistry in the first place?
So one of the key things about chemistry, I think, is its diversity. So the different areas that it can apply into. So although I'll talk about carbon capture today, that's one research area of my one area of research in my group. But the other area I work in quite a lot is actually cosmetics. We do a lot of work with renewable materials, putting naturals into cosmetics and things like that. I'm really trying to do it from the scientific perspective. So we have a little company called Keracol that does that. And we have some products made by a Dr. Kraft brand that's actually available. And to actually have a career where you can be as diverse as that. I'll talk about power stations today, but another day I could tell you all about, cosmetics with natural products in there and stuff like that. So, having something as diverse as that is really, really interesting. And, from my perspective, it's a very, very fascinating career. Lots of different things I can get involved in.
Oh, cool. Well, sounds great. And actually, it sounds like you could very well be a very rich source of quantum sources into the future. But let's deal with one at a time. Today, we're going to talk about the capture of carbon dioxide then. So maybe I could get you to share your screen and we'll look at a presentation from yourself.
Absolutely. Here we go. What I want to tell you about is some of the work we've been doing at the university and through my spin-out company, C-Capture. Basically on carbon capture and storage, and this is where we're capturing carbon dioxide before it's emitted into the atmosphere, and basically storing it usually underground, where it can stay for thousands of years and help mitigate CO2 emissions and climate change. And so I'll tell you a little bit about what we've done on the lab scale, but also then some of the work we've done where we're starting to scale this up in a power station.
Okay.
So what do we normally do? We're normally dealing with CO2 separation. So this is quite a common technique in industry. And you normally have a feed gas stream and then some sort of chemical process which separates whatever is in your feed gas stream, usually carbon dioxide, and then everything else. And this really relies on CO2 reacting selectively and reversibly with what we call a solvent, whereas any other gases, so oxygen, nitrogen, they just pass straight through.
So you've almost got a chemical filter being applied.
Absolutely, yeah. So it just sucks out the CO2 and lets everything else come out the top of a big chimney, as you'll see. So once you've done all of that, you've captured your CO2. What can you do with it? Well, this slide shows you sort of 5 things, really. The various storage things. You can put in a saline aquifer, for example, a big hole in the ground. You could put it into unminable coal seams. You can use it to enhance oil recovery. So you push it underground and that will push oil out of the ground so you can get more efficient oil recovery. Perhaps not the best thing in the longer term, but certainly in the short term, you'll see it's been quite a useful approach. Or you can put it in depleted oil or gas reservoirs. And that's really what the UK is probably going to do. There are some rather large depleted oil and gas reservoirs up in the North Sea. And so that's where we're likely to stick a lot of our CO2. Final one is utilization. So obviously, if you can do something with that CO2, if you can utilize it, maybe make some chemicals with it, or make your fizzy drinks, your fizzy soup or whatever, and so be it. The only problem with that is the scale that we have to do this on is actually much, much larger than reasonably we can actually use. So there's going to be a lot of storage as well as the utilization, if we can do. So Sea Capture is a spin-out from the university, established in 2009 from the University of Leeds. And really, we wanted to create the most energy-efficient CO2 capture solution through chemistry and engineering innovation. Sounds very grand, but bottom line with all this is chemists need to work with engineers very, very closely to actually make a process that really is going to work and is going to be able to scale onto a very large scale. So this is all about chemists and engineers working very closely together. Chemists can't do it on their own. Engineers can't do it on their own. We need to all work together to actually get this to work. And on the right there, you'll see Rose and Fatima. Rose is one of our leading chemists. Fatima is one of our engineers. And they're actually on site there of our demonstrator at Drax Power Station that I'll show you a little later on. Okay. The key thing about all of this is to create a solution which is viable on a large scale. This has to be done on an enormous scale if we're really going to do it. Capture millions of tons of CO2 every year. So this can't be tiny little bits of chemistry. It's got to be something that will work on a very, very large scale. And when we first started doing this, it was an interesting idea, interesting concept. We never really thought we would get quite to this stage. But, in principle, what we can do now is make a significant contribution to saving the planet. The technology is developing such that I think in the next 5 to 10 years, it will reach a stage where it can actually make a significant contribution to combating climate change. Okay. So what do we do? Basically, we have what we call a solvent. And a solvent is a liquid. And these kinds of things have been around for a long time, really since the 1930s. So this is a patent from the 1930s, where basically you can use a similar approach to actually separate CO2 and hydrogen sulfide from natural gas. So when natural gas occurs in the ground, it's not just natural gas, there are other acid gases mixed in with it, so particularly CO2 and hydrogen sulfide. And there are this class of compounds called amines, which are inherently basic, and they react with CO2 and hydrogen sulfide, which are inherently acidic, to actually sort of, if you like, capture them, to hold on to them. And then you can actually regenerate the solvent and you get your natural gas in a relatively pure form. So that approach has been used for carbon capture and storage because we're still reacting with CO2. We still want to take CO2 out of a gas stream, but one of the problems is the gas stream now is very different. So instead of having methane in there, you've got other things like oxygen, impurities maybe from coal combustion or biomass combustion, and all these things can actually impact on the capture process and often catalyze degradation of these amines and things like that. The other important thing here is the scale. So natural gas sweetening, as it's called, has been done on a pretty large scale for many years, but we're probably going to have to do it on maybe an order of magnitude larger scale, for example. And that's a big jump in terms of scale. So when we first started this work, we were aware that there are challenges with amine-based solutions, particularly in contact with things like oxygen and metal impurities, because the metal impurities can catalyze the oxidation of these amines. So we wanted to develop a different technology which didn't have these inherent problems.
Are those problems simply due to, that they become problematic because it affects the efficiency of the process? Or when I think of like oxidization and throwing oxygen into the mix, I almost think of explosive mixtures. But what is that actual risk?
It's not explosion. It is, as you say, it's a gradual deterioration. And what happens is the amines that would normally react with the CO2, over time, they react with the oxygen. And once they've reacted with the oxygen, they can no longer capture the CO2.
Okay.
And so they become less and less efficient over time. One of the key things, if you've got a very large capture plant, for example, on a power station, what you don't want to have to do is keep filling it up with more amine and more amine, because you very rapidly use an awful lot of amine if you're not careful. And so you want the solvents to last as long as you possibly can. So you want to minimize that degradation, so minimize its susceptibility to oxidation, which is really one of the main problems here.
Okay.
And so here is our unique source. I did promise we would show you our source. So this is Doug, who's our head of chemistry, Doug Barnes, and he played the leading role in the discovery of our source. And basically, you can see it there. You can say that you've seen it. I'm afraid, like all the best sources, the recipe is a very closely guarded secret. But that is our secret source there. That's my bit, and that is what we put in the as you say, in the demonstrators, and it's really good stuff.
I'm going to go out on a limb and say that this is possibly the first recommended source on Quantum Source that couldn't be described as either edible or drinkable.
It's biodegradable. I wouldn't recommend you drink it or eat it or put it on your chips, but there are compounds very similar to it that people do put on chips, for example.
Okay, right.
So we have spent a lot of time on this, trying to make it as environmentally benign as possible. So one of the issues with amines, for example, is some of them, not all of them, some of them are actually pretty nasty, and you wouldn't want to put that anywhere near your chip. The kinds of chemicals that we work with are actually much more benign, and indeed that's one of the main advantages of our process, because if you're doing this on a very large scale, you want to minimize any risk due to hazardous chemicals or anything,
environmental contamination and things.
Absolutely. So that's been very high up on our list of priorities over the last sort of 5 or 10 years. So it might seem a little bit not quite in keeping with the normal source, but actually there is a lot of stuff behind it that actually makes it much more benign or much more user-friendly, if you like.
Absolutely. Anything goes on Quantum Source anyway.
I'm glad you said that. Okay, so this next slide just tells you a little bit about how it all works. And so what we've got is your power station. You see that on the left. It could be any source of some sort of flue gas, any sort of gas stream that's got CO2 in it. So although power stations is what often people think about, there are numerous other sources like, for example, cement manufacture, iron and steel, hydrogen manufacture, power generation, but burning other things besides coal, for example. Waste to energy is a big one these days, where you're burning waste to actually reclaim some of the energy from that. Natural gas, and potentially oil as well. There are lots of things you can burn, and they all give you, this flue gas with CO2 in it. And so what you do is you blow that flue gas up the bottom of the absorber. So you can see we've got two parts of the process, one that says absorber on it, one that says stripper. The absorber is basically essentially at 30 to 40 degrees centigrade, so it's cool. And as your flue gas goes up, what happens is you've got a solvent that is our secret sauce, if you like, is raining down the absorber. And as it comes down, it picks up the CO2. So by the time it gets to the bottom, it's picked up all the CO2 that was in the flue gas. Whereas the flue gas keeps going up, blowing up the top, and eventually it comes out of the top to be mainly oxygen and nitrogen. And of course, all the CO2 will have been taken out, and that's now stuck in your source at the bottom of the absorber. So you then pump it round through a heat exchanger. So it's big cool, but we need to warm it up now. So that heat exchanger helps warm your source up before it gets into the stripper. And stripper is basically where you heat everything up. And at about 100, 120 degrees, something like that, what happens is the CO2 now comes away from the secret source and basically then comes out the top, and that can then go to a compressor where it's pressurized, and then that can go off to storage. So you've got your solvent now, or your source in the stripper. The CO2 has come off it. It comes down to the bottom. This is where we actually use a lot of the energy in the process, in that you have to heat up the solvent in that stripper and we get that heat usually from say a power station, maybe a steam cycle from the power station or any other source, and that's what we call a parasitic load, because it does take quite a lot of energy to enable you to do that. And so once all that CO2 has come off, you can then reuse your solvent. And the whole point of this process, you've got a nice cyclic system where the solvent carries on going through the system continuously, and that's why this issue of degradation or oxidation crops up, because you're actually pumping the solvent through for months, actually, if you can get away. Yeah, and over that sort of period of time, even though the reactions with oxygen might be quite slow, if you're doing a reaction for months, then actually it can become significant over time. So, as I say, applicable to a wide variety of gas streams there. Key thing about our solvent, our technology, is the parasitic load. So I've mentioned a bit about the benign nature of the solvent, but also the amount of energy you use. And amines have been used for a long time, and quite often when they've been used, energy use hasn't really been an important consideration. So MEA, for example, that was the first amine that was used, monoethanolamine, first amine that was used in the 1930s. And if you put that on a capture process, it typically uses about 3.7 gigajoules per ton of CO2. So joules is a measure of energy. Gigajoules actually means lots of energy, essentially. And for every ton of CO2, you would use 3.7 gigajoules. So that was where things were quite a long time ago. Over the years, there's been quite a lot of incremental advances where people have started to use mixtures of amines to optimize the performance. So they call these amine blends. And if you use those, you can get down to about 2.7, 2.8 gigajoules per ton. So a significant chunk off the MEA. And so the area C capture is working in at the moment, we're on about 1.8, 1.9 gigajoules per ton. So that's pretty much half of what the original MEA would require. So, that's a major saving in terms of energy use. And that's a key operational expenditure, if you like, for the likes of a power station. All that energy that you're using actually effectively reduces the efficiency of your power station. So the minimum you use, the better. And so, as well as the energy use, as well as the environmental credentials, these are the things that really come together to actually make the technology something quite different. We call it transformational because it is underlying, its chemistry is actually fundamentally different to what has been done before.
Sure,
and when you change things that much, then you can get the different performance, and that's really the key thing there. Okay, so now some pictures of the technology where we are. You can see how we've come from relatively small scale. So on the left there is a fume hood with a piece of kit that we use routinely called a vapor liquid equilibrium analysis setup, which basically will measure the solubility of CO2 in your solvent at different temperatures and pressures. And that's really the first pass, if you like, in working out whether a potential solvent is any good or not, whether it's worth taking to the next sort of scale. If you then look at the next picture, that's what we call a mini plant. That's where you're looking at something that would look at on the scale of roughly a kilogram of CO2 a day, maybe a little bit more than that. And then the last two slides are actually biogas trials where you can actually get a lot more CO2 in biogas. You can use the same technology to take CO2 out of biogas to make biomethane. And you can see there 100 kilograms and 1,000 kilograms or a ton on the far right there. And you can see the scale of the absorbers. So the absorbers on the left, on the right there are actually much bigger because of the amount of CO2 you need to capture. So on the next slide, this is where we're looking at the sort of scale. So we've come from the grams of CO2 per hour to the kilograms. What we're doing it now, or just finishing off, is a full pilot demonstration of around a ton of CO2 every day, that sort of order of magnitude. And then what we're now doing is developing plans to start to think about how we would put together something that would work on 100 or 1,000 tons per day. And as you'll see later on, the sort of scale we need to do if we're going to put our technology on Drax is 10,000 tons a day.
Okay.
So that's a 10,000 times increase or multiplier on essentially where we are at the moment. So that's quite a challenge as to how we're going to do all of that. So the next slide shows you again the insides of the biogas demonstration unit. You can see Doug Barnes there again on the left, our head of chemistry. Dave, one of our process operators at the back, and Gergely, who actually put a lot of the electronics in place for this. But you can see that the large absorber in the center there, that's basically where the CO2 mixes with the solvent as the solvent trickles down from the top. And at the back, you can't actually see it because it's black, but there is the stripper unit, which is hot, but that has to be insulated, so it's got lots of black foam around it, which actually insulates it, so you can't actually see it. But it gives you an idea anyway, the sort of scale. So this is actually in a shipping container, and the kind of things that we're on now. This is the next slide. It shows you where we are out on site at Drax. So again, shipping container, but you'll see now we've got some pipes, large pipes coming out the top. Those are our absorber columns, and basically what we've got now is a demonstrator on Drax. It's been running for quite a long time now. It's allowed us to learn a huge amount about scaling up our solvents and how to develop the technology so that we can scale it to the next size. And basically, you can see the shipping container, but at the back, you can also see a very large pipe. And that's actually the flue gas ducting for one of the boilers at Drax.
Wow.
So if we just press the next slide, you can see at the moment, the pipe, the flue gas that comes into the shipping container has about a 10 centimeters diameter, and we've got to go from that to the size of the flue gas duct behind you. Yeah. So this is the thing where we're going from, say, one ton a day up to 10,000 ton a day. That's the sort of engineering challenge now that we're facing. And sea capture ourselves, we can't do it because we're a small team of 15 or 20 people, something like that. But we are now working with other companies who really know how to do these things, and that's where we really are at the moment, looking at the scale up to get to the sort of scale that is really, really required.
And that's that bridge that you were talking about between chemists and engineers. You've got the chemical process, and that needs to be engineered up to the bigger scale.
Absolutely, and of course, there's chemists and engineers working on our demonstrator here. It's actually quite a different skill of engineering, again, taking it to the next sort of level where you're building things that are, almost, they're actually very large chemical engineering production plants, essentially. Huge bits of engineering, and that's another skill set in itself. So it is working its way through the scale. So it is quite a challenge there. Yeah. Okay, so Drax is a very big power station. It's about 6% of the UK's supply. I think it goes down a little bit depending on the weather, whether it's windy or whether it's sunny and all this sort of stuff. But it is one of the UK's main power stations. And one of the key things about Drax is, they have been very innovative over the last sort of 10 years or so, and that they now use biomass as their fuel, or predominantly biomass as their fuel, instead of coal. And that allows you to get into the concept of what we call negative emissions. So on the next slide, you'll see essentially what we've been doing for the last 100 or 200 years is we've been digging carbon out of the ground. So it could be coal, it could be oil or whatever. We're burning it to generate energy. And when we do that, we generate lots of CO2, and that CO2 ends up in the atmosphere. Well, with BECCS, or bioenergy with carbon capture and storage, essentially it provides a mechanism to do exactly the opposite. So what you've got in the atmosphere around us, of course, at 400 parts per million and going up all the time, is you've got lots of CO2, and through photosynthesis, basically that CO2 comes together and produces trees, essentially. And so what Drax do is they use parts of the tree that are essentially waste, and they make wood pellets, and those wood pellets then go into the power station. You can burn them, generate heat, and if you capture that CO2 now and you bury it underground, you can see essentially it's a mechanism for transferring CO2 from the atmosphere underground. So it's the reverse of what we've been doing. So there are lots of caveats you have to add to this. So, for example, you've got to make sure that when you grow trees, you don't, that doesn't involve too many other CO2 emissions, maybe with fertilizers or transportation of your pellets and things like that. You've got to minimize the CO2 emissions associated with the whole of the pellet manufacture, and also, of course, with the capture process as well. Yeah. But if you can minimize that, then this concept is actually pretty viable. It's recognized by the Climate Change Commission, for example, and also the IPCC as a valid method of trying to have what we call negative emissions. And there aren't that many good ways of negative emissions along the lines of this. Yeah. And so, a lot of people think that CCS, it doesn't really happen. Well, this is a picture of a power station in Texas, Houston, Texas. This is the Petronova plant. And basically, this has had CCS on it for the past 4 or 5 years. And so what they have is one boiler where they take roughly 50% of the flue gas from that boiler and put it through a CCS process. So the next slide, you can see the plant. So the very large tall tower on the right is the absorber. So that's where you've got your amine, or your amine source, if you like, trickling down and capturing the CO2. And the small silver tower on the left is your stripper, and that operates at much higher temperature. And then once you've captured your CO2, in this particular case, what happens is the carbon dioxide is transported in a pipeline under pressure, probably about 50 to 100 bars, something like that, to an oil well roughly about 80 miles away, and it's pumped down and it helps them get the oil out of the ground. There are, of course, issues with that approach. It's not a sustainable long-term use for the CO2, because actually, we're moving away from petrochemicals. But in the short term, what it does, and it's very important that it does, it actually helps demonstrate the carbon capture technology, helps demonstrate it on scale, and it provides some sort of incentive, some sort of financial return. Because at the moment, just storing carbon dioxide under the North Sea, nobody's paying for that. Yeah, and at some stage, that things are going to have to change so that will happen. But in the short term, actually using it for enhanced oil recovery is what happens in this particular case.
And I would guess that you could also, monitor it to make sure that it's not leaking out. Once you have stuck it down there, it's not leaking through cracks in the ground or something like this and ending up just back in the atmosphere again.
Absolutely, yeah, and there's been lots of studies on that sort of thing. One thing to remember that is anywhere that has got natural gas or oil in it usually has been that gas has been underground for probably millions of years.
Yeah.
And so that infrastructure there, and then it's usually under pressure. So that infrastructure there, if you like, that geological feature is actually going to be very strong, and it's going to be pretty much set as long as it's capped off properly. Then you should be fine. I'm not a geologist, but I know a few geologists. I am reliably informed that this is a viable process and stuff. In fact, the Norwegians have been doing it for probably the last 25 years off the North Sea and the Sleipner field. So they've been doing this for quite a while, and so Norwegians are actually quite a way ahead in some aspects of CCS technology, and indeed CCapture has been working with some of them to help with that technology as well. Okay, so finally, just to say a little bit about net zero, how we're going to get there. Of course, we need to fundamentally reduce global emissions wherever possible, and a lot of that will come from renewables. If the wind's blowing, great, sunshine, absolutely fine, but there's a pretty much definite acceptance these days that we can't do it without carbon capture and storage. It's going to be a key part of the transition. So all part of the mix. We've got to do everything basically as large and as large scale as we can, as quickly as we can. And CCS can be used to reduce emissions from sectors which are usually hard to decarbonise. So things like cement, iron and steel, glass and ceramics, waste to energy, hydrogen production, all these sorts of things that currently are very large industrial processes. We can use our technology to actually decarbonise them. And of course, one of the holy grails is these negative emissions technologies such as BECCS. They're going to be required. If we're going to be net zero, we can't get everything down to zero. There's going to be some positives still there. So we need some negatives as well to offset that. And it is sort of the likes of BECCS that will allow us to do that sort of thing. And, I think the key thing there is the CCapture technology, very well placed to make an important contribution here. So last slide is just to show you a few of the people involved there. In the middle of the slide, the picture, you can see Tom White, who's our CEO. Tom joined us earlier this year. On the far left, you can see Doug Barnes, who's head of chemistry, PhD student with me and only many years. He's led all the chemistry activities in CCapture. And the chap at the front on the left with the lab coat on is Casper Schulderman, who's the Director of Engineering, and he's led most of the engineering expertise as well. He's been with us for the best part of 10 years too. So those two really have led this, and of course you can see the rest of the team now growing all the time. So I'll say thank you for your attention there. One last point, there is Helen Atkinson, who's our business development manager. So if anybody's got any specific queries about CCapture, particularly from the more commercial side of things, then Helen is well worth dropping an email. She's very friendly and she'll usually engage with you. I should also acknowledge our investors. So IP Group have been with us for over 10 years. So they helped provide some funding to start off with, but have been ongoing with other funding. Drax also recently, and BP. And we've had quite a lot of money from Bays over the years as well. They've all been incredibly supportive in getting all of this off the ground. So thanks for your time, and I hope that was okay, Adam.
No, absolutely, Chris. Thanks very much for your contribution to Quantum Source. I'm really happy to see that the secret sauce is really making some advances. So good luck with the next phases. What I would just say is that we've seen that the Norwegians are pumping CO2 into Sleipner. Then you showed us the example in Texas. What do you think the likely fate eventually of the CO2 from Drax would be? Would it be an onshore solution, do you imagine, or would it also get pumped into a North Sea reservoir somewhere?
It's very much offshore, yeah.
Right.
So, the way the government is doing it at the moment is doing it in clusters. And so there's a northeast cluster, for example, and a Humber cluster. And basically what we've got is lots of energy, lots of large-scale industrial CO2 producers around in those areas. And basically they will all feed into the same CO2 pipeline, if you like, and that'll go up the east coast, and then it will go off and it will go into the North Sea. I think it might be Goldeneye. I can't remember, but there is a field up there that there's quite a few that people are looking at very, very closely.
So thanks again, Chris. We'll leave you to your afternoon now. Just what I would say to the Quantum Source and Be Curious audience is that you've seen some contact details in Chris's talk. Equally, Chris and CCapture are on Twitter, and I'll be tweeting them from the Quantum Source Twitter account. So if you do have questions, I'm sure that Chris would be happy to take them from you.
Of course, yeah.
Great. Absolutely. Well, thanks very much again, Chris, and we'll leave you to your afternoon and say goodbye.
Cheers, Adam.
So thanks very much to Chris for satisfying some chemical curiosities. And what I would say is that even as a member of a university department, I still get amazed how interconnected everybody's research is. You get Chris with his chemistry, but it branches off into engineering, into geology, into sustainability, and it just really snowballs. And I think that's a really great thing about universities. Now, if you enjoyed that, you can keep your eyes peeled on the Quantum Source Twitter and Instagram feeds, where there's already loads of videos from the lockdown summer to keep you educated and entertained. If you're looking specifically for Be Curious content, then hashtag BeCurious2020 is the thing to look out for on Twitter. You can also search for Be Curious on the University of Leeds web pages. Just remains me to say that I've been Dr. Adam Booth, this has been Quantum Source, and you've been great. Stay cool, stay curious.